Assalamualaikum and a very good day. I be to our supervisor, Professor Dr. MURUGESAN THANABALAN, and our internal examiner, Dr. Serene Locke. In this video, my group will be presenting about our plant design project entitled Plant Design for Offshore Liquefied Natural Gas LNG Plant. Before I proceed with my presentation, let us go through the overview of our presentation. Me, NURUL AFIQAH Muhammad Maksum with the ID number of 23977 will be in charge to present about the introduction and preliminary hazard analysis. Ladies and gentlemen, although naturally occurring gas has been known since ancient times, its commercial use is relatively recent. Natural gas consisted of primarily methane with a trace amount of carbon dioxide, hydrogen sulfide, mercury, and water. In addition, it is considered to be environmentally friendly as compared to other fossil fuels such as coal and crude oil. Its combustion emits negligible amount of sulfur dioxide and lower emission of carbon dioxide and nitrous oxide. Natural gas is normally used in liquefied state and it has been conventionally processed on shore. However, in 2013, the landscape in LNG industry changed when the first floating liquefied natural gas facility is launched. FLNG is an offshore facility that produces, liquefies, stores and transfers energy by using carrier ships. It is located in open water and exposed to the prevailing sea state conditions. The advantages of this FLNG is it is more environmentally friendly compared to onshore LNG processing. And we have been given a problem statement that requires us to remove contaminants, especially carbon dioxide, hydrogen sulfide, mercury, and water through the pre-treatment process. The objective of this project is basically to apply our fundamental chemical engineering knowledge in heat integration, process control, process safety, and also economics to design our offshore LNG plant. For feed and product properties, the feed consists of hydrocarbon constituent and non-hydrocarbon constituents. For example, hydrocarbon constituent consists of methane, ethane, and propane and also butane. For non-hydrocarbon constituent, it consists of hydrogen sulfide, carbon dioxide, and mercury. Natural gas in its pure state is colorless, shapeless, and odorless. It is a combustible gas and according to SPITE in 2015, it gives off an enormous amount of energy when burned. Natural gas is a very safe source of energy when transported, stored and used. It has been used for residential, commercial and industrial heating use. Most of the usage comes from industry, which is about 56%. For the market demand, we can see that global gas demand trend is actually increasing by year, and in 2020 it is expected to be 50 billions of cubic feet of demand, and the same trend can be observed in global gas production. Approximately 400 billions of cubic feet is expected to be produced in 2020. And the statistics from BP Energy Outlook 2030 shows that the production of LNG is still more than the demand, which will never result in insufficient LNG in the market. For LNG production in Malaysia, we can see that the trend is fluctuating. However, in recent years, the trend is actually increasing, with last year as the largest LNG production, which is about 28.69 million metric ton LNG being produced. Talking about global energy export, Malaysia is actually one of the key players in the global energy exports because it is the third largest energy exporter in the world and the second largest oil and gas production in Southeast Asia. For plant location, we have come up with 3 possible plant locations, which is at offshore Kelantan, offshore Sarawak, and also offshore Sabah. And we have done some research on a few criteria, which includes raw material supply, availability of labor, market availability, climate, utilities. Criteria including local government incentive and transportation does not show significant differences among each other. And from the table, we can see that the highest mark goes to Sarawak. Therefore, it is preferable to set our FLNG in offshore Sarawak because of various good reasons, but for the most important reason is because it has the largest natural gas reserve, which is about 52.88 ton square cubic feet. Moving on to the preliminary hazard analysis, LNG possesses a few chemical hazards. If it is released, it can form a vapor cloud formation that is flammable when mixed with air, and it also has high radiant heat hazard than other flammable liquids. It has the risk of explosion in confined spaces, especially in liquefaction plants, and also rollover can happen with resulting in the formation of boil-off gas. For inherently safer designs, there are 4 principles to be applied with each, which is the first one is substitution from the harmful substance to less harmful substance. In this case is the substitution of MEA to MDEA, because MDEA is less harmful than MEA. And the second one is the minimization of the size of vessel and pipelines. Moderation involves lowering the concentration of our chemicals, and also simplification is being done in the reduction of equipment. And last but not least is the local safety regulation and design guidelines. And through this gas regulation, the government and natural gas industry are expected to be responsible in ensuring the reliability, efficiency, and safety of the liquefied natural gas. And I think that's all from me. I will pass to my friend KHALIDAH to proceed with the presentation. Thank you.
Thank you, AFIQAH. I'm KHALIDAH AMANINA and I will explain about conceptual design analysis. Okay, technology selection. First, slug catcher. Basically, slug catcher is used to separate gas and liquid. There are 2 types of slug catcher, which are finger type slug catcher and vessel type slug catcher. Based on the comparison, vessel type slug catcher is chosen because it is simple in design, easy to maintain, and require less installation area compared to finger. Installation area is indeed a significant factor in deciding which type of slug catcher, as FLNG has limited space for its operational unit. Next is mercury removal unit. Mercury needs to be removed in order to prevent corrosion to the plant equipment and avoid the deactivation of downstream catalysts. These are the differences between non-regenerative mercury adsorbents and regenerative adsorbent. Based on the comparison, we choose to install non-regenerative mercury adsorbent before the acid gas removal unit and the hydration unit. This is to prevent any contamination of mercury in the rest of the plant. Besides, the concentration of mercury in the feed gas is low. We use activated carbon as the adsorbent as it has great ability to adsorb mercury. Next is acid gas removal unit. It is to remove acidic components such as CO2 and H2S. CO2 is removed to avoid freezing in the cryogenic exchanger, and H2S is to meet the sales gas specification. For this unit, we choose to use amine technology because it is a matured and widely used technology, and MDEA is chosen as the adsorbent as it has low corrosiveness and high resistance to degradation. Next is dehydration unit. It is used to remove water from natural gas in order to prevent the formation of hydrates, to avoid corrosion, and to meet the requirement of water content in water in product. There are some choices for the dehydration unit, and we decided to use molecular sieve with 4A sieve. 4A sieve is more stable and has higher water uptake capacity. Then I will proceed with liquefaction unit. Liquefaction unit is in natural gas, involve the condensation and cooling of natural gas, and we decided to use refrigerant system as it has simple process. There are various types of refrigeration system such as this. After comprehensive comparisons, we decided to choose nitrogen cycle, nitrogen expansion technology as it is suitable for our targeted production. Also, it is not flammable, which gives a safer condition for the production of LNG and reduce the need for inventory of flammable components. Basically, it is safe. As you can see, it is safe, stable, insensitive to motion, simple in operation, ease of maintenance, and minimal operator interaction. Next, I proceed with design alternative. There are 3 design alternatives, and we decided to choose the first alternative. This is because we need to remove mercury first instead of acid gas and water. The effect of acid gas and water is not as adversely as of mercury. Therefore, we will install a mercury removal unit, acid gas removal unit, and dehydration unit. So we will cancel all the alternative 2. So let's look at alternative 3. The difference between alternative 1 and alternative 3 is the addition of acid gas removal unit by using membrane. The hybrid system is an effective method to remove acid gas effectively. However, the acid gas in the feed gas is too low. Therefore, it is not recommended to choose the hybrid system in order to minimize the initial capital investment of the plant. Basically, and then I will proceed with mass balance. This is the composition of the feed gas, and basically for the mass balance, mass in need to be equal to mass out. And we use this formula and several assumption for manual mass balance. The feed flow rate is 16500 kg per hour. And for the slug catcher, the liquid and gas is separated and the difference is charged 2.22% between manual and HYSYS. For mercury removal unit, we able to remove all of the mercury for both manual and HYSYS. For acid gas removal unit, we assume 98% of CO2 and 100% of H2S removal for manual calculation, and we managed to remove 100% of H2S and about 99% of CO2 for HYSYS. The difference for the stream 5, which is sweet stream, is only negative 2.39%. For dehydration unit, we assume 97% of water removal for manual, and we managed to get 99% of water removal for HYSYS. Therefore, we managed to get 218925 kg per hour of 99% of methane with difference of negative 3.82%. That's all for me, and I will pass the floor to Heng.
A very good day to Professor Murugesan and Dr. Serene. I'm Jian Heng, and now I'd like to present about the economic potential evaluation of this plant design. So basically, economic potential is to analyze the profitability of a process plant. Now, let's first take a look at the economic potential 1, which refers to the net revenue after considering the raw materials costs. This table shows the total revenue generated is at 5.79 billion ringgit Malaysia, while the total cost of raw materials is at roughly 612 million ringgit Malaysia, and hence the EP1 value obtained is 5.18 billion ringgit Malaysia per year. And now, let's move on to the economic potential EP2, which is the net revenue after deducting the cost for both raw materials as well as the utilities. Before heat integration is done, the EP2 calculated is 1.45 billion ringgit Malaysia per annum due to the heating and cooling duties of the plant. After heat integration is done and heat exchanger is introduced to the system, the total consumption of the utilities got reduced and the EP2 becomes slightly higher at 1.59 billion ringgit Malaysia per annum. And this actually shows a 9.33% reduction in the total cost required, and this also indicates that the design definitely has a great feasibility to generate profit in the future. Next, I'll move on to the process flow sheeting of the proposed LNG plant. The process starts with the slug catcher unit, where it acts as the primary separator. The natural gas comes in saturated form, and the slug catcher is used to remove slug from the natural gas. The feed gas is then channeled to the mercury remover unit. For mercury remover, activated carbon is used as the non-regenerative adsorbent, and this is the operating condition for the mercury remover adsorption tower. And next, for the acid gas remover unit, it actually involves two stages, which are the absorption of acid gas followed by the regeneration of solvent, which is the MDEA. So, in this remover unit, carbon dioxide gas and hydrogen sulfide gas are being captured in the absorber, and the top product of the absorber is identified as sweet gas. The bottom product of the absorption tower will flow through the stripper for regeneration purpose, where the lean amine solution will come out as the bottom product and then recycled back into the absorption column. And these are the operating conditions for the acid gas remover unit. And next, it will be the dehydration unit, where water is removed from the natural gas stream by the means of adsorption process by using molecular sieve, and the operating condition is shown in this table. And after dehydration unit, the natural gas stream will flow through fractionation unit, where the heavy hydrocarbons will be separated into individual products by distillation. Demethanizer, deethanizer, and also depropanizer are among the three fractionation units proposed, where methane, ethane, and propane could be separated accordingly based on their boiling points. And these tables show the operating condition for the fractionation process unit. After that, methane with purity of 99.2% is obtained successfully through the demethanizer unit, and it will be condensed to liquefied natural gas in the liquefaction unit. Nitrogen expansion cycle is used, and the liquefied natural gas is cooled down to a temperature of negative 162 degrees Celsius, where it becomes a liquid in order to obtain the maximum volume reduction. And this table shows the operating condition used for the nitrogen expansion cycle. And lastly, the cool liquefied natural gas would then be obtained through the end flash separator with this operating condition. Now, I would like to proceed to the heat integration of the plant. Heat integration is carried out through pinch analysis by using the Hint software. So, pinch analysis is also known as a process designing method, at which it helps to maximize the heat recovery and also to minimize the overall energy consumption. It is also used to optimize the utilities and to reduce the operating cost of the plant, whereby the heat rejected by a particular unit could be used by another process. So this is basically the summary of the 4 streams data that we use for the heat integration for this project. Let us take a look at the heat exchanger network and the heat cascade. So, based on the heat exchanger network design generated at the delta T mean of 10 degrees Celsius, we can actually observe that one heat exchanger is introduced to the system along with one heater and another 2 coolers, while the heat cascade diagram shows that the pinch temperature is at 45.21 degrees Celsius. And this would be the composite curve from the heat integration, and this is the grand composite curve obtained and generated from the Hint software. And let us take a look at the comparisons of the utilities consumption. These are the changes of hot and cold utilities after heat integration. As for the changes for hot utility, we can actually observe a 8.67% of reduction, while the cold utility has a reduction of 23.87%. The data also shows a duty reduction in approximately 100,000 of kilowatt, which 12.72% of heat is recovered through the heat integration. Alright, so this is the process flow diagram of the plant before heat integration with the cooler and also the heater. And this is the PFD of the plant after heat integration, where the cooler is removed and the heat exchanger is introduced to the system.
Hello everyone, I'm SHARVINAA will be presenting on the process control and instrumentation. It is important in a plant to maintain the quality and performance of LNG product. It is also crucial to control the operating parameters and to ensure the safety precaution of the plant. There are 3 types of variables involved in the control strategy. The first one is control variable, that is independent variable that usually not influenced by external factors. The manipulating variable is the dependent variables that are affected by controlled variable. The disturbance variable is the variable that directly affects the process output but cannot be controlled by control strategy. Moving on to the process control strategy for separator. The level controller is to maintain the level of the liquid, and the controlling variable is the liquid level. MV is the flow rate of the bottom product, whereas the disturbance variable is pressure of inlet stream. The strategy for both is the feedback. And the objective of the pressure controller is to maintain the outlet pressure of the gas, and the controlling variable will be pressure of outlet. MV is flow rate of inlet stream, and DV is flow rate of inlet stream. Moving on to the distillation column, there are few indicators and one controller in the distillation column. First one is flow indicator to indicate the flow rate of the inlet stream with the controlling variable of flow rate of inlet stream. There is no manipulating variable and disturbance variable for indicators. The next one is the flow rate indicator to indicate the flow rate of inlet stream with the controlling variable of temperature of inlet stream. Next is the pressure indicator to indicate the pressure of the column with the controlling variable of pressure of the column. Next one is to indicate the temperature of the column with the controlling variable of temperature of the column. The temperature indicator is to indicate the temperature of the condenser inlet stream with the controlling variable of temperature of inlet stream. The next one is the temperature controller. It is to control the temperature of the outlet stream of condenser with the temperature controlling variable of temperature of outlet stream of condenser with the MV flow rate of outlet stream of condenser and the DV flow rate of inlet stream. And the objective for the temperature indicator is to indicate the temperature of reflux stream with boiler, and the controlling variable is the temperature of reflux stream of the boiler. Moving on to the absorption or absorption column. There are three indicators and two controllers. The first one is temperature indicator. It is to indicate the temperature of inlet stream, and the controlling variable is the temperature of inlet stream. And next is the pressure indicator. It is to indicate the pressure of the inlet stream with the controlling variable of pressure of inlet stream. The next one is flow rate indicator to indicate the flow rate of the inlet stream with the controlling variable of flow rate of inlet stream. The next one is the liquid level controller. It is to maintain the level of liquid with the controlling variable level of liquid. The MV is bottom product flow rate, and the disturbance variable is pressure of inlet stream. And finally is the pressure controller. It is to maintain the outlet pressure of the gas with the controlling variable of pressure of outlet. The measuring variable will be pressure with the manipulating variable of flow rate of the inlet stream, and disturbance variable will be flow rate of inlet stream with the control strategies of feedback. Moving on to the compressor. It has speed controller. It is to control the outlet pressure of the compressor with the controlling variable to the pressure of the outlet. The manipulating variable will be the speed of compressor with dV of the flow rate of the inlet. Moving on to the cooler with the temperature controller with the objective to maintain the cold outlet temperature, and the controlling variable is stream temperature with the manipulating variable is flow rate of hot inlet, and dV is temperature of cooling water with the strategy of feedback. Moving on to the storage tank, the objective is to maintain the LNG level in the tank with the controlling variable of liquid level. MV is flow rate of bottom product, and dV is pressure of inlet stream, and the strategy will be feedback. Moving on to the PIND diagram for after integration with the controllers and indicators. Thank you.
Hello and good day. My name is AHMAD and I will present on the safety and loss prevention and the plan layout of this project. Okay, for the safety and loss prevention part, we are required to do hazard and operability study, or also known as HAZOP. The purpose of doing HAZOP is to identify the hazards and to assess the operability of the plant when there is an occurrence of deviation, and HAZOP is done based on the review of NID. How HAZOP is conducted is, first we have to separate or divide the PNID into smaller sections, or we call it nodes. We can divide the nodes according to its unit's operations. Okay, HAZOP also involves guide words, and we use the guide words to assist in the HAZOP process. For the HAZOP, the underlying theory is consideration of hazard occasions that are caused by deviations from design or operating intention. Deviations is the combination of guide word and parameters. For example, the parameter used in this HAZOP is flow, pressure, temperature, and level. So, okay, the example is like this. No less is the guide word, and the parameter is flow. So the deviation will be no or less flow. So we use this kind of deviation to assess the hazards and to assess the operability of the plant. Alright. Alright, first I will show you how we conduct the HAZOP. First, this is the first node, which is the slug catcher. Okay, as you can see, the green line is the node for slug catcher. Alright, so we have seen this, then we go to the next. Alright, so this is the HAZOP worksheet. We have deviation, cause, consequence, safeguard, and action or recommendation. Okay, first the deviation is more flow. The cause of more flow is in the valve fail and start open at the slug catcher. So as you can see, the consequence will be causing overpressure and possible rupture of vessel, leading to LOC and fire is ignited. So the safeguard already installed at the slug catcher will be the pressure indicator controller. This will detect the high pressure and control the valve. We will give recommendation if the safeguard is inadequate. So the recommendation is to install high and high pressure alarm at slug catcher to alert operator. And the second one will be to install PRV to depressurize the vessel in case of overpressure. If you can see, the deviation for more flow and more pressure is quite the same. It have the same consequence, has the same safeguard and recommendation. So for the more level, alright, so for the more level deviation, we have the cause will be CV1045. This is the valve for the water outlet, fill and start close. So when there's no outflow of water, then the level in the slug catcher will be high. So yeah, it will lead to overpressure, possible rupture, and LOC. So the safeguard that we have is level indicator controller. Okay, so the recommendation will be to develop the standard operating procedure for intervention of the valve during emergency to prevent process upset. And then we also install a high and high level alarm, high pressure alarm, and PRV. This is just the same recommendation as the above recommendation. Right. So this is basically the example of how we conduct the HAZOP. Alright, so this is the note for note 2, which is the mercury recovery unit. Alright, this is the recommendations that we get from the HAZOP. Develop SOP for intervention and operation during emergency, which means that the company need to develop a standard operating procedure to manually close or open the valve during emergency, and then to install high and high pressure alarm, install PRV, and then install low pressure alarm. Next will be Note 3, which is the acid gas removal unit. Yeah, basically the recommendation is quite similar, but which is to develop SOP, to install low temperature alarm, install high temperature alarm. But the recommendation is quite similar, but at different places on the PNID or different places on different unit operation. Alright. Next is Note 4 for dehydration. Still the same recommendation. Develop SOP, install flow indicator, install high and high pressure alarm. This is all quite similar recommendation. Okay, this is for Note 5 is fraction. Still quite the same recommendation. Okay, this is Note 6, which is the liquefaction. Generally, all the recommendations are quite the same, which is to install low level alarm, high level alarm, to develop standard operating procedure, and to install PRV. This is the common recommendation given to all the unit operation in the plant. Okay. The detailed and complete HAZOP can be obtained from the full project report, and it is also included at the end of this slide. So now we move on to the plant layout. Okay, as you can see, this the number one, the green square is the inlet facility, which inclusive of the slug catcher and the separation process system. Okay, from this we move on to the pre-treatment system, which is the AGRU, acid gas removal unit, mercury removal unit, and dehydration. This is where we conduct the pre-treatment process. And then we move on to number 3, which is the fractionation. This is used to separate methane from the other heavy hydrocarbon. And the last one will be liquefaction and storage. As you can see, we have diverse and open longitudinal escape routes, which is at the side of the facility, and we have additional central corridor at the process deck. And then the accommodation for the staff or the living quarters will be located far away from the process area, because it will be too dangerous for the staff to be living near to the process area. And the location of the flare will be located as far as possible from the process and the living quarters. The flare will be placed in the turret area due to heat flood considerations. Okay, that's all from me. Thank you. Now I will pass the floor to SHARVINAA.
Moving on to the conclusion and recommendation. As for the conclusion, a detailed and comprehensive plan design for FLNG facility was successfully proposed. The plant would be located in Sarawak due to its rich gas field and strategic location. The chosen design alternative was successfully simulated through Aspen HYSYS. 99% of LNG purity was successfully achieved at targeted annual production of 1.5 million tons. The purity of both ethane and propane was above 90%, so it can be sold as side products to obtain higher revenue for the plant. 12.72% of heat was successfully recovered with duty reduction of 100,556 kilowatt through heat integration. The plant has an economic potential value of 1.6 billion per annum, indicating the feasibility of the project to be able to generate profit in the future. As for the recommendation, the first one would be unrecovered hydrocarbons such as methane, ethane, and propane could be further processed and recycled back to the fractionation unit to obtain higher yield and purity of LNG and NGL. Next is the cooling system in the liquefaction unit could be replaced by cooling water and or fuel fan cooler so that the overall energy consumption would be reduced to lower range. And finally is the acid gas removal could be expanded with a hybrid system of membrane separation in the future to enhance the absorption process of carbon dioxide and hydrogen sulfide. Moving on to the references, and these are the references list that used in this project. So that's all from us. Thank you.